And there are a lot of ingredients that go into the conformal bootstrap, so I thought it might be useful to spend at least the first part of the talk giving an introduction to what goes into the conformal bootstrap so that everyone can follow along. And then in the second part, I'll focus on explaining some of the most exciting results that have come out of the conformal bootstrap program, and also where we're going from here. So CFTs and conformal bootstrap. So let me just start with a little bit of motivation for why it's interesting to study conformal field theories in more than 2 dimensions. So why study CFT in greater than 2? And okay, there are a number of reasons. One reason is that CFTs are the basic building blocks of all quantum field theory. In the sense that almost every quantum field theory that we know about can be thought of as some sort of interpolation between a scale invariant structure at short distances and a scale invariant structure at long distances. So there's a very general sense in which quantum field theory can be thought of as a flow from a CFT in the ultraviolet to a CFT in the infrared. Of course, in many cases, the CFT in the infrared, if the quantum field theory is a gapped theory and there are no massless excitations at low energies, then the CFT in the infrared could be completely trivial, could be empty. But we also know lots of situations where you can have very, very non-trivial behavior at low distances, and if we want to classify the different possible types of behaviors, then that's something that conformal bootstrap is very good. Another motivation, of course, comes from the ADS CFT correspondence, where there are lots of different ways you can think about it. But from my perspective, we're going to be focusing on learning, what can consistent unitary conformal field theories do, and what this is going to tell us is, what do UV complete consistent theories of quantum gravity look like? So there's a very real concrete sense in which we can learn about quantum gravity and string theory. By pursuing the conformal bootstrap. On a more sort of practical, down-to-earth level, CFTs also show up all over the place in the real world. Okay, so in particular, continuous phase transitions in both statistical and quantum systems are usually described by conformal field theories. So this is true in both 2-dimensional systems and 3-dimensional systems. And so one example that I want to mention now and then come back to later is the 3D icing model. And this is a 3D CFT which shows up in many, many different systems. But one place that it shows up is if you look at fluids in the real world, like water or liquid helium or almost any fluid you can think of. It has some temperature pressure phase diagram. And there are lines separating the solid phase from the gas phase and the liquid phase. Solid, liquid, gas. But the line separating the liquid phase from the gas phase ends at some critical point. And in a wide variety of fluids, the physics at this critical point is universal. It always looks the same. And that universal structure, which has emergent scale invariance, and in fact an emergent conformal invariance, is described by the 3D icing. In a field theory language, we can ask what is the 3D icing model. Well, it's what you get, or at least we believe it's what you get, if you take a scalar field in 3 dimensions and give it a chordic interaction, and then adjust the chordic, the coefficient in the chordic interaction to some critical value, lambda critical, while also tuning the mass of the scalar to be 0 at the quantum level. Okay, this is a strongly coupled theory. The critical value of this coupling is an order 1 number. But there are various ways people try to get a handle on it. One approach is to look at phi to the 4th theory in 4 minus epsilon dimensions, and then you can find perturbative fixed points in the epsilon expansion. And then you have to try very hard to figure out how to extrapolate epsilon to 1 if you're using the 3D theory. But another approach to learning about this theory is the conformal bootstrap, and that's what I'm talking about. Okay, so that was my brief motivation. So now let's talk about what a conformal field theory is. So I apologize if I'm repeating things that everyone's heard before. But okay, what is a conformal field theory? Well, it's a quantum field theory with conformal symmetry, and in these dimensions, the conformal group is SO d, 2, or SO d plus 1, 1, depending on whether we're in a Lorentzian or Euclidean signature. Okay, both of these cases are interesting. From the perspective of the conformal bootstrap, they're more or less formulated in the same way. So we can talk about both of these situations. And okay, of course, the generators of the conformal group consist of translation generators, Lorentz rotation generators, as well as generators of scale transformations and generators of special conformal transformations, KDU. And once you have all these generators, you can start classifying operators according to how they transform under the action of all the generators. And in particular, if you start thinking about local operators, well, they can be labeled by their scaling dimension delta, which is the eigenvalue of the action of D, and some set of spin quantum numbers, which are their eigenvalues of the action of M. Further, you can break up the local operators into primary operators and descendants. Okay, the primary operators are the ones that are annihilated by the special conformal generator at the origin. And the descendants are obtained by acting on the primary operators with some number of translation operators. Which when you do this, what it gives you are derivatives of the approach. Okay, so this is CFT 101. Let me also mention that usually we're going to be interested in unitary conformal field theories. And so one of the important constraints constraints in unitary conformal field theories are that all the states in the conformal field theory have a positive norm. And the condition that states have a positive norm places restrictions on the allowed values of the scaling dimensions of the primary operators. So in unitary CFTs, you can, for example, require that all descendant states have a positive norm, and this forces the dimension to be bigger, greater than or equal to d minus 2 over 2 for scalar operators, and L plus d minus 2 for spin L operators. And these conditions are very important to keep in mind when thinking about applying the conformal bootstrap to unitary CFTs. Maybe I should mention that what do I mean by a spin L operator? This is an operator which is a traceless symmetric tensor under the Lorentz. Okay, any questions so far? Okay, so now we can ask, all right, what constraints does having a conformal symmetry place on the correlation functions of local operators? And it has a number of immediate consequences. So one immediate consequence is that the expectation values or one-point functions of local operators vanish. It also tells you that two-point functions of an operator have to take form, which is completely fixed. Okay, so there's some numerator which depends on the spin quantum numbers of the operators, divided by the denominator, which only depends on the separation of the two coordinates. This is shorthand notation for x1 minus x2, to the power of 2 times the scaling dimension of the operator. x2 is x1 minus x2. Okay, so 1-point functions are 0, 2-point functions are completely fixed by conformal symmetry. 3-point functions are also completely fixed, or almost completely fixed by conformal symmetry. So in particular, if I look at 3-point functions between two scalar operators, phi of x1, phi of x2, O u1 through ul of x3. Okay, so 3-point function between two scalar operators and a spin L operator. Then, okay, you think about the action of the conformal group on this correlation function, and if you work it out carefully, you'll see that the form of the 3-point function is also completely determined, and up to some overall coefficient, lambda phi phi o, times, okay, again, there's some numerator, numerator, which is a product of factors carrying the Lorentz indices, divided by a denominator, x1, 2, to the 2 delta phi minus delta plus L, x2, 3, to the delta minus L, x1, 3, to the delta minus L. And this is completely fixed in terms of the scaling dimensions and spins of all, and the spins of the operator. Okay, so maybe I should mention there's a very useful formalism for arriving at these kinds of results, which is sometimes called an embedding space formalism. And what is the embedding space formalism? Well, the idea is that instead of writing things down in terms functions of the d-dimensional space. I can work in a d plus 2-dimensional space where okay, the metric is the S of d comma 2 metric, or S of d plus 1 comma 1 metric. And the action of the conformal group is linearly realized in terms of the embedding space coordinates. And if the action of the conformal group is linearly realized, then it's very easy to write that invariance. Objects which are invariant under conformal transformations, it just corresponds to Lorentz invariance in the embedding space. And then, so what you can do is just write down all these embedding space Lorentz invariants and then project back down to d dimensions. In order to project back down to d dimensions, if I have some embedding space coordinates which run from 1 to d plus 2, then in order to project onto a d-dimensional subspace, I need to impose two constraints on the embedding space coordinate. And a way to do this is by restricting yourself to, first of all, the section where x squared is 0. So that's one condition. This puts you on a null cone in the embedding space. And then I need one more condition to project back down to 2 dimensions. And the way you can do this is by identifying xa with some constant times xa on the null cone. So this is sometimes called the projective null cone. So these two conditions project you down to a d-dimensional subspace, which you can identify with ordinary space. And this is a very useful formalism for deriving all these results.
Yeah. Sorry, the conditions are uniquely defined. I mean, can you take other conditions, or they unique?
Oh, this is the only way I know how to do it.
Okay.
Yeah. I mean, you can, right? You want your conditions to be covariant under the S of d comma 2. So another possibility would be to add some constant to the right-hand side of this equation, but that would end up projecting you down to anti-de Sitter space or de Sitter space. So there are other ways to do a projection,
Which are meaningful, but
which are meaningful but don't
I see.
and
Okay. Okay. Thanks.
Yeah.
Also, sorry, another.
Yeah.
For sure, is a completely stupid question. The fact that in the 2-point function you put the same operator, and in the 3-point function you put, because if I put two different operators, they go down to 1-point function. I mean, they factorize.
Good. So the 2-point functions between different operators
Yeah.
necessarily vanish.
Okay, because it's factorized, and so I can see as a 1-point function times 1-point function. They vanish.
Well, it doesn't necessarily factor. It doesn't necessarily factor.
Okay, but they vanish.
But yeah. So if you write down by two different operators and you write down the general form of the 2-point function consistent with translation invariance, rotation invariance, scaling invariance, then you do see that there is some structure. But then the constraint
I see.
under the special conformal transformations forces these two operators to have the same scaling image.
I see. Okay, thanks.
Yeah. So all of, or at least a lot of the non-trivial structure here is coming from the fact that these are primary operators, and we're demanding that they're annihilated by a special conformal generator, and that's really where you gain a lot from this embedding formalism, because the constraints of all the other symmetries are fairly easy to do. And I might say more about this later when. general, you can consider 3 operators, all with different spin quantum numbers, and then it's no longer the case that the form in general is completely determined. But for any set of 3 operators, you'll find some finite number of allowed tensor structures in the 3-point function, and each of those tensor structures comes with some undetermined coefficient. So more generally, the 3-point functions aren't completely fixed, but they're determined in terms of a finite number of parameters. Now, knowing all these 3-point functions is equivalent to knowing the form of the operator product expansion. So once I know these 3-point functions, that's the same as knowing the form of the OPE. So in this example, if I look at a product of 2 different scalars at different points, then I can re-expand this in terms of all the operators in the phi cross phi OPE. And these are the same thing as all of the operators that have non-vanishing 3-point functions with phi. And there's some overall coefficients in the OPE, which are the same as the 3-point function coefficients. And then there's some function of the separation and derivatives acting on the operator O, evaluated at one of the points. So then the claim is that this function is also completely fixed by conformal symmetry in terms of the scaling dimensions and spin quantum numbers. One way to see that is by taking the OPE, plugging it in to the 3-point function, and then demanding that this differential operator C, acting on 2-point functions, reproduces the 3-point function. So you can solve that condition order by order in the separation and see that this function is completely fixed. So that's nice because it means that now that we know this OPE, we can use it to evaluate other correlation functions beyond the 3-point functions. In particular, we can use it to evaluate 4-point functions. And then the only and in particular, then we can start evaluating all of the higher point functions in terms of this basic set of CFT data, these OPE coefficients and the scaling dimensions and spins. Then the only lingering question is whether this gives us convergent expansion. But fortunately, in conformal field theory, there is a very sharp criterion for when the OPE is a convergent expansion. And the statement is that the OPE is convergent if it can be interpreted as a change of basis in the context of radial quantization. Okay, so let me write that down. If it is a change of basis in radial quantization is a shunt. So what does this mean? So this means if I first of all fix an origin and I quantize my theory in terms of spheres, successively bigger spheres surrounding that origin, and I write down radially ordered correlation functions. So phi of x, some number of insertions, phi of x, phi of 0, vacuum, where I'm putting the things closest to the origin on the right and things furthest from the origin on the left. Then, by the state operator correspondence, operator insertions at the origin acting on the vacuum generate a complete basis for the Hilbert space, the CFT. Okay, so this gives me phi of x acting can write this as an expansion and a complete basis for the Hilbert space of CFT. Some coefficients times some function of x and derivatives acting on the states of both. So this is a convergent expansion, just by the completeness property of the Hilbert space. And that means that here I was safe in using the OPE to evaluate this correlation function. An equivalent way to say it is that if I have my subset of insertions, so some operator the origin, some operator function x, and everything else is further out, then as long as I can draw a sphere surrounding these two operators where no other insertions are inside that sphere, that's the statement that this is radially ordered, then the OPE is a convergent expansion. So, is that clear?
Essentially follows from state operator to form.
That's right. This follows from the state operator. Okay, so now that we have the OPE, we can use it to evaluate 4-point functions. So let's just do the simplest case by 5x1, 5x2, 5x3, 5x4. Well, first we can ask what are the general constraints of conformal symmetry on the form of this 4-point function. And okay, if you think about it, you can do this, ask this question in this embedding space formalism. You'll see that the general form looks like a product of 2-point functions, 1 over x12 to the 2 delta phi, 1 over x34 to the 2 delta phi. That's certainly a valid 4-point function. That's what I would get if I did some Wick contractions on this 4-point function to say something is factorized. But then on top of that, there could be some arbitrary function of conformally invariant quantities. And in fact, when I have 4 points, there are 2 conformally invariant cross ratios that I can build out. So this u and v appearing in this function are quantities that I can build out of the 4 points, x12 squared, x34 squared, x13 squared, x24 squared. And v is the same thing, but with 1 and 3 permuted. And this combination is invariant under any conformal transformation. So we have this big ambiguity in the 4-point function, which is that we don't know what this function is. Fortunately, we can now that we have the OPE over here, we can use it to evaluate